Okay, so what about now? Let's record it. Record. All right, so I hope it's recording. Okay, so it's this one. Uh, let's quickly do the uh, this week's workshop. You successfully really participated in your workshop, so let's get that deeply. So in the quiz of this week, it was very easy. It was just two questions. Yeah. All right. So it is talking about the Eulerian cycle. So Eulerian cycle is the graph such that, okay, uh, you've got a cycle, and and it doesn't repeat edges, but the Eulerian cycle adds some feature, and it's this one. Every edge has to be repeated exactly just one time. Just one time, every edge, exactly one time. It has been inherited of the definition of cycle. Eulerian cycle just tells you that you need to use every edge. Okay, so every edge has to be uh, used Eulerian. Uh, Now, Hamiltonian, while Hamiltonian is about every vertex. So you might have one cycle in the or graph in your graph, but if you use all edges, then it's Eulerian. If you use all vertices, then it's Hamiltonian. It's possible to have a graph both Hamiltonian and Eulerian. So Hamiltonian, every vertex, just one time. Every vertex of the graph has to be used. All right. So let's analyze question one. Question one says that whether it has got Eulerian cycle or not. So we see that if I start from the PC1 here, I won't be able to come back to PC1 because there is just one edge. So it's impossible. Even if I start from somewhere else, I have to pass from PC1 vertex, but there is only one edge. All right. So uh, this means this is not Eulerian. Okay. A is not Eulerian. Hamiltonian. So if I start somewhere, I need to pass PC1, or if I start from PC1, I need to come back from PC1. In any condition, there is server vertex here. I need to pass this one server. Okay. So this server will be the reason of not being Hamiltonian. So say Mac2, Mac1 server. If I go here PC1, then I have to come back server and touch again and go back to the Mac2. So number one, this edge is repeating. It's okay in Hamiltonian, but since you repeat the server, this means the graph is not Hamiltonian. Okay, so A is not Hamiltonian. Now let's have a look at the graph again. So Mac 1, Mac 2, server, and PC. Okay, we see that the server, if I eliminate server, the vertex, then all the incident edges will be eliminated. So this means server, the cut vertex in the graph. Okay, so it can't be the reference of graph. Is be a Hamiltonian. A Hamiltonian graph cannot have a cut vertex. Now, let's have a look at the other part. Okay, so what about this one? Sydney, Melbourne. So there are two airlines from Sydney to Melbourne. So one airline from Melbourne to Christchurch and one to Sydney. All right, so what about this one now? If I try to have Hamiltonian, well, it's easy. A cycle, I discovered a cycle inside this graph. Okay, so it does use all vertices just one time except the Melbourne in starting and ending point. The cycle that I highlighted for you, it doesn't use this edge. So it's okay in Hamiltonian. Hamiltonian. But part B is not a not an Eulerian graph. Because anyway, if I start, I have to come back here. But or in this cycle, it doesn't use this edge. So which is problem in Eulerian being Eulerian. However, we will see one criteria that saying that in Eulerian, graph, every vertex degree should have even degree. So let's analyze. Degree of Melbourne is 1, 2, 3. What do I mean by degree of the Melbourne is how many edges have been attached to the vertex Melbourne. Well, this one is 3, obviously. With the same reason for Sydney vertex or city, the edge is 1, 2, this one, 3. Degree of Christchurch is just 2. Okay, so what the Eulerian graph here is not Eulerian graph because not every vertex is even degree. The degree of the Melbourne and Sydney is not even. Now, back here, part C. We see now here, quickly, I'm able to draw a cycle, which is repeating all the vertices except the first one just one time. So this means it is a cycle repeating vertices just one time, and so this graph it is a Hamiltonian cycle. Consequently, we can call this graph Hamiltonian graph. So part C is a Hamiltonian graph. Now, WH, CH, go, J. So look at this one, this one, this one, this one, this one, this one, this one. Okay, so I couldn't find a. What about this one? Starting from here, this can be just canceled. Why? This one here. If I have to use this one, so I don't go back to James. So chance. So it's not Eulerian. It's not an Eulerian. However, degree of we can see that degree of Whitehall is what? 2. Because we see that 1, 2. Degree of chance is 3. So I found my first odd degree. So this means the graph, you don't need to analyze the rest if you are after only for Eulerian feature. So it's not Eulerian graph because you found at least one odd or non-even degree. Let's continue. And degree of Jade, degree of Go is just 2. Degree of Jade is 1, 2, 3, 4, 5. All right. So we have now, we are in the place to start with the question 2. Question 2 says that whether this graph has got Hamiltonian path or Eulerian path. Well, question 1, part A, yes. And let's add degree of is 2, degree of Mac 2 is 2, degree of server is 3, degree of PC1 is 1. We can see that we can start from here 1, 2, 3, 4. Okay. This one is not, it's a path which is Hamiltonian and which is, it's not Hamiltonian. Sorry. It's not Hamiltonian. But what I did, it was Eulerian path. So this is, it has got Eulerian path. However, to see that a graph has got Eulerian path or not, you need two odd degree, exactly two odd degrees, 3 and 1. One of them will be for start and the other one will be end. So this one, this. It's Eulerian path. For the Hamiltonian path, I have to start from these guys, Mac 1, Mac 2, server, PC1. So it has Eulerian and Hamiltonian path. What about this guy? This guy, since it has got Hamiltonian cycle, it can be counted as Hamiltonian path as well. You just don't need to go to the end. Means starting from here, just here, it's Hamiltonian path and it's enough. This can, but for the degrees, this guy, degree Melbourne 3 and Sydney. So starting from here, back here, it is, and here is a Eulerian path. In Eulerian path, you need to meet all the edges, okay? But starting from the 1 degree odd and ending in the second odd degree, okay? You can start from here and ending here as well. So this has both Hamiltonian and Eulerian path. Okay. What about this one? Yes, it has got degree 5 since it is Euler Hamiltonian cycle, so it is easily can be constructed the Eulerian Hamiltonian path. But for Eulerian path, start with the degree 5, jail, this one, this one. Then go here, chance, ending in the next odd degree. All right, so now question 2 is also done. So imagine this is your graph here, and this is the vertex going here. So we see that this vertex is a cut vertex. Why? Because if I remove this one, the graph will be disconnected. So it's a sensitive vertex or it's a cut vertex. If you remove it, it will be your graph will be disconnected. Now, therefore, if I try to, so I'm saying that let's assume that this is Hamiltonian cycle, but if I make Hamiltonian cycle here, if I start with this one, then if I go here and come back, I won't be unable to come back here. And also this is a cut vertex because to go back to this side, and maybe there is more. Okay, maybe there is more. I need to pass this this vertex. Otherwise, this is not it. If I am able to come back from somewhere else to this branch, then this is not a cut vertex. So this means this graph is not Hamiltonian. So how to write this question? To answer this question, you will write, let's assume that we have a Hamiltonian graph which has got, by contradiction, a cut vertex as well. If I wanna try to have cycle, I need to pass that cut vertex and come back as well. If I pass through that cut vertex here, come back from here, then my graph is not anymore Hamiltonian. But if there is another way from coming back from uh, uh, this branch or somewhere else, or going just use this cut vertex one time, then this guy is not cut vertex anymore. So in both scenario, you will have contradiction. Okay, like this one. You won't get this question in your mid-semester exam, which will happen not next week, the week after. But it's good to have such examples so you will grasp the idea. Now, stay here. And there is something about Hamiltonian graph. You know, it's very easy to understand the Eulerian graph. There is a good criteria for that. So for determining that whether a graph is Eulerian or not, you see that every vertex has to be even. But for Hamiltonian, it's not easy. One of the famous criteria is that you're given that the number of vertices that you have got in your graph is more than 3, and let's say it's n. If every degree of the graph it's like more than half of the number of the vertices, then that graph is Hamiltonian. So the question is asking us to create the 5 vertices. Okay, 5 vertices. So this means n is equal 5, and the question actually asking us to create such a graph such that degree of those 5 vertices has to be more than half of 5. 2.5 can't be a number, but it has to be 3. So let's see what happens. 1, 2, 3. It's 1. 3, this. Okay. This is the planar graph because the edges are not cutting each other without vertices. So can we count this one? What's the edges of this one? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. Okay. So this is Hamiltonian. This is really Hamiltonian. Can we try to make Hamiltonian graph? Okay, I failed. How do I do this? Okay, now I'm good. So I was able to, so I do it again. Okay, like this one. 2, 3, like this. I can start from here as well. Oh, no. This is a path, but yeah. Okay, this is Hamiltonian cycle. The other example, okay. All right, so every vertex has got degree 4, so which is more than 3. So this is complete graph K5. Okay, so what's the Dirac's theorem? If every degree vertices is more than a half, then the graph is Hamiltonian. But now, this one, P, then Q. And we say that that's true, so we will show it by this. That's always TT, true. But is this one is correct as well? Okay. If Hamiltonian, oh no. If a graph is Hamiltonian, then every vertices of graph has got degree more than half. Okay, more than half of the vertices. Okay, is this true? No, since we can make a counter example. What is the example? Let's go back. 5 vertices. G is a graph with V and E, like this one. Okay, so this is n equal 5, but each degree is not 3. There is at least one degree such that the degree of that vertex is less than 3. This guy is called C5. This guy is K5. This is just a random graph, a planar graph. This is called almost like a pentagonal pyramid if it's a geometry. Now here it's C5, all right, C5, and the degree of each one is 2. 2. Even if you draw this one, this will be 3. Still, it's a counterexample because not every vertex is 3. If you draw this one, it's yeah. It's Hamiltonian cycle, but it still doesn't satisfy in this claim. Okay, so this situation, the assumption here, hypothesis here is very heavy condition. It's more than enough. But on the internet, you can look up exact criteria, sufficient and necessary. Probably you won't find anything. Probably there is. I don't know about the last update. You can get something better than this, but probably you won't find exact reason, exact necessary and sufficient. This is sufficient. It's like excessive. It's more than enough, this condition. Now, is there any question about this? Otherwise, we go to the next question. We see that a weighted graph is like such graph such that the edges, it has got extra feature, and every edge has got some number or positive number, positive value, which is called weight as well. So it's called weighted graph. Let's say like this graph, 4, 1, 2, 3. Yeah, probably it can be a expenditure of traveling through those two cities or two vertices, or time. Okay, these are time, expenditure, money that you need to spend. It's a weighted graph. So every wedge, the adjacency matrix of this one, it's like you draw the adjacency matrix of this one. And if you remember, the adjacency matrix was you will get 1 or 0 in the adjacency matrix, which you did in your assignment as well in the question 4 part B or part A as well. But instead of, if it is 0 means there is no edge, but if it is not 1, it can be Not one, not only one, it can be more numbers, 3. So here, let's say this is A, B, C, A, C. 1, 2, 3, 2, 0, 4, 3, 4, 0. So let's do this one. A, B, C. A to A is 1. A to B. A to B is 2. A to C is 3. All right. B to C is 4. All right. So I don't need to analyze the rest of that because it's undirected graph. It is possible to have a directed graph such as like this one, but it's undirected graph, so it is symmetric. All right. Uh, so here means symmetric means this part upper triangle is mirror of the lower triangle. 4, 4, 3, 3, 2, 2, 1. To be able to answer this one, you didn't need to go through all the lecture note. This part, this box was enough. This box was enough. So traveling salesman problem, or what do you call the guy that is going home by house and delivering the letter? What's that called? Postman? What's that? What do you call the guy that going to house by house and deliver the letters? Huh? Is there any other special name? Okay, so once upon a time, I wanna, yeah, there was a postman going to the villages and deliver the letters. He was like curious to uh calculate the shortest path, or let the least expenditure, the least time that he or she spending to deliver all the letters. All right. So it's called Chinese postman problem, but here is written traveling salesman problem. It's the same. You can look up that. So asking the minimum weighted Hamiltonian cycle. He or she wants to visit the villages or houses just one time. Okay. So Hamiltonian cycle in a graph. The name comes from the situation it is used to model that traveling a salesperson. Here is traveling salesperson who wants to visit all the cities in region exactly just one time. Return to where he or she started and traveled a minimum distance in the process. Same thing. Now, we have the adjacency matrix of a weighted graph for this one, K4. K4 is a graph with 4 vertices, simple graph with 4 vertices with 3 degree 3 for each vertex. All right. So if I find what's the Hamiltonian cycle of this one? 1, 2, this one. It can be this one. It can be this one as well. In any way, other way. Yeah, there is no other way. So let's write for. So let's write all the weights that we used. 5, 1, 4. All right. Uh, let's write. What's the summation of the weights? 1 plus 4 plus 4 plus 5. It is 14. What about this one? 4 plus 3 plus 2, 9 plus 4 is 13. What about this one? 5 plus 3 plus 2 plus 1 is equal 11. So the efficient Hamiltonian cycle is this one. But this can be very complicated if you have more vertices. You should have good method to be able to do this one. Sometimes it's possible you work in city council or municipality and you want to design the bus route. You want to have the bus should have a Hamiltonian cycle and visit all the bus stations just one time. I I don't want to ignore the other like this the opposite side of the road. We can treat it as different vertices. All right, so this was question 6. I know it's very easy for you. Let's do this one. Right. So question 7 is about the explanation that is given to us in the box. All right. So n cube, qn or n cube is a graph which is isomorphic with the following description. The vertices are all possible binaries. So with the length n. So give me an example of length 2, binary length 2. Me a number which is binary and its length is just 2 digits. Are you guys studying computer science yet? So what's the binary? Okay, give me a number which is just 2 digits of that. Yes. What is? 1, 0, what is? 2, excellent. What's the fourth one? Okay. Can we have more than these 4? All right. So all possible all possible binary length n. So how many vertices do we have? If n, capitalized N is equal to, means length is 2. Just 4 of them. So this means 2 power 2 means 4. What are the vertices? Vertices names, I already said that to you guys, but the vertices are A1, A2, A3 until A power 2n. One until A2 power n. And each vertex AI is the combination of 0, 1, length n. So given that we have these vertices, how do we connect them? You describe your graph, not only vertices, you need to describe your edges as well. So edges between any two vertices will be drawn if and only if the vertex is string or 0, 1, 0, 1, 1, 0, 1, 0, the binary stuff, the binary things, they are different exactly in one place. Okay, so for example, here 0, 0, 1, 0, 11, 11. So you see 0, 0, 1 in Q3, in 3 cube, 3 cube. So cube 3. So because therefore the binary has got length 3. This will be connected to this vertices 0, 1, 1 because the only difference is the middle guy. Middle place. So see, this is the same. This has to be the same. The only place, one place is the middle one. Okay, so a binary with length 3. You want to listen to me as well. Today I just took it easy. Yeah, do you feel it? Yeah. All right. What was it? Please turn it off. Okay, look at this one. A binary with length 3. This like number 0, 1, 0, 1, 0, 1, A, B, C. This can be like connected to another vertex here. Here, if just one of them are different. So this vertex can be connected to this vertex if it's this different with this or different with this, different with this. So in the Q3, the binaries are shiny. Okay, don't do that. They can be connected if they are different in one of the places. Here, here. Okay, so the possible one for a binary in Q3 is just degree 3. So let's go one example here. N equal 3. So Q1 is just this one. And the names are 0, 1. They are in one place. There is only one place and they are different. So they will be connected. Can't have Q0. Q2, we can have 0, 0 as you said. So 0, 0 connected with 1, 0. This can be connected to 11. This can be connected to 0, 1. This can be connected to this one. This just for the name is cube. So let's just do it neatly. All right. What about Q3? Q3, it has to be cube as well. So let's call this one 0, 0, 0. 0, 0, 1, 0, 0, no, 1, 1. So 0, 0 to 0, 0, 1. This can be 0, 1, 0. This can be, this guy will has to be 1, 0, 0. All right. So this vertex can be connected to one of the other vertices as different places. Here 1, or here 1, or here 1. So that's why here, here, and here. So the rest will be automatically corrected. So I should have better started with this one. So at first one, I put 0, 0 here, then immediately 0, 0, 1, the adjacent vertices. Then after, we can make the other ones such that here is 0, 1, here, 1, 1. 100, it has to be different with 0, 1, 1. No, it can't be because it's already used. It's already here. Can be 1, 1, 1, 0. Can be, this can be, what about this one? 1, 0, 1. Can be 1, 1, 1. Yeah, we are done. Okay, we are done. So the way that we make is this one, immediately these three. So 1, so 4 of them made. So after this, if you make the other 3, 2 or 3, you'll be able to find the other ones as well very easily. And this is Q3. Q4 needs 4 dimensions, but still in the graph theory, you can do it. Okay, so Hamiltonian cycle Q3. Okay, can we find Hamiltonian cycle here? So I will go here. Okay, finished. Okay, so I can do it again. And here, then I come back here, go up, roam around, and here, and come back down by elevator. That's Hamiltonian cycle. So each degree, each vertex has degree 3. So it's not, each degree is not even. So it's not, you cannot make Eulerian cycle. Let's have a look at the other question. A function which is one-to-one and onto, it's called bijective function, or totally together it can be called bijection. So to have bijections, you need to have function one-to-one or monotone or injection. Injective function is called injection, and surjective function or surjection. Three one-to-one functions are important. Just you can easily look up any report on the internet, one application of one-to-one functions in computer science or in computing. So there are applications for one-to-one functions. All right. So what about this one? Let's find question part A. F, Ben, Daniel, Chris. So Ben related to because of this guy. Daniel related to John's. Chris. Oh, John. No. Okay. So when we have function, when this guy, when we don't see such scenario from if we see such scenario, it's not a function. So we don't see such things. And if we see something like this one, it's not in the range. If we see something like this one, it's not one-to-one. So we don't see these things, these scenarios. So it is function and it is one-to-one. It covers all the range. So the range of the function is from F to here. And so this one is covered as well. So it's onto as well. So this function, okay, is bijective. The last one. Now the birth year function on the F Ben, let's do this one. Ben, and I, no, it's 1979. Okay. Now this time function is defined from this domain to this range, Z. The images of the function can be different. Daniel. Oh, sorry. 1979. And Chris born as well in 1979. So we see this one that we see such scenario here. So it's not one-to-one function, and also Z function is not covering all the Z. So the function is not onto. So it's just function and it's not bijective function. All right. So part A, part B, part A here and part B here, but not function. If we see something like this one, not one-to-one. If we see something like this scenario. All right. So next, Next things that we can talk about. An isomorphism between two graphs G and H is a bijective function on such that f there is a function which is bijective function between the vertices of the G and H, and it is bijective function between the edges, or it preserves the structure of the edges like this one. By the help of this definition, we can construct the isomorphism function between the graphs. All right, so instead of question 9, it's too much. Let's do question 11. So isomorphism functions, we want to know that which two graphs are isomorphism. So to reject the isomorphism, structure can be shown in the degrees of the vertices. Like here, you see this one here. The degree of this one 3. The degree of this one is 2, 2. While in this graph, all of them turn it off. 3, 3, 3, 3. So one of your quizzes question, second question, saying that are these two graphs are isomorphism? Well, it was easy. You didn't need to prove it. It was just sufficient. Question 2 with 2 marks. Saying that since one of the graphs has got vertex degree vertex 2, but the other graph doesn't have vertex degree 2. So G, so the graph G and H are not isomorphism, are not isomorphic. But the graph F and G are isomorphic. Because, okay, have a look at here. From F, you see this one. Better to pay attention. This is sensitive thing. M, okay, degree 3. F, all of the F are degree 3. It's hard. So we can relate everything to from H to F, but you need to be careful to preserve the structures. How do we do this? I'm giving you a constructive method, which you might miss, or lecturer did not say this one. 2 years ago, I was the lecturer of this course. I had many complaints, but okay. I should have been more like kinder with the students. Anyway, I'm kidding. No, I was lecturer, but yeah. So M, H, Look at this one, H, the vertex M, and I just choose this one by chance. It's degree 3 and that one is degree 3. If it's not working, I can correct myself. So I will relate M to A, but now M connected to Q, M connected to N, and M connected to P. So I will write the Q, I will write P as well. I will write N as well. Now connected to C, E. So I will write Q, C, P to E, N to which one? B. All right. So M is connected to Q, P, N. So in the same time, I wrote C, E, B. So I related these vertices to P, N, Q, and P. Now let's move to a O. So O. So from there is O, and O is related to P. It's already chosen. So O. So here as well. So let's not use this one. Okay, so this one is chosen. I'm going to choose this F. All right, so F. So let's not use Opera. So I will use R here, R, and it's related by Q. So Q is related by C, and C is here, and I will choose D. I repeat again, I chose R. R is connected to N and Q, and so I choose D. Okay, so from Q to C, Q is for related to this guy C. Q goes to R. C also goes to D. I will write this one, but I need to probably to see this guy D is for the R. D goes to E, then E has to be N. N is not that one. Okay, I will write B here, E here. Okay, so the rest, which one is not chosen is F. So F is here, and the other one has not been chosen is O. Okay. Okay. Now we need to check if the preserve or structure of the edges are chosen. How come? Oh, let's use different color. Now look at this one, M to N, and we need to choose M to N is here. And is there any edge between A and E? Yes, it's here. So A and E is also chosen. There is edge between A and E. Now M and Q, there should be A and C, which there is. So I'm changing my color. Between M and P, uh, I made a mistake. I have seen something wrong, like, oh, this nuts. When I was choosing, when I was seeing M connected to Q, O, and N. Okay, you could correct me. So I thought that M is connected to P. So this will make a lot of problems. O, P. Okay, let's hope that there is no problem. M and O is connected, and I wanna see that if A and B is connected. Yes. All right. Uh, I checked N. Now I wanna check Q. Q is connected to, changing my color, Q to R. I wanna see if there is structure between edge between C and the corresponding C and D. Where is that? C and D here. And D. Yes, there is. There is. Okay. Q. Did I check Q and O? No, I can check now. It's here. Q and O. Is there any between C and B? Yeah, it's here. Okay, I wanna see the how many graphs did I check? M. I can clean everything here. So don't mess up in the mid-semester exam. Don't mess up. Don't write it on that because you will need it again. So I checked my M to Q to O, M to N as well. Now I checked Q to O. All right, it preserves the structure. Uh, I checked QR. Okay. What else I need? I would like to check this guy. This R2N. R2N, it's this one. I wanna see if there is edge between D, E, and D. Yes, there is one. Which edges has been left now? If you could help me. NP. Okay. I will write NP and use blank. NP. So where is the NP here? NP. Is there any edge between E and F? Let's see. E, F. Yes. Okay. Now, what's the other possibility? I have just need to check two of them. So let's do this guy. P, O. O. So I want to see that if there is edge between B and F. B, F. Yes, there is edge between B and F. Okay. Last one. Last one. PR. So PR, is there any edge between D and F? DF. See? DF. DF. Okay. So yes, we investigated that this function works. Okay. So F M to A, F Q to C, but in the same time we see that the edge FM, let's say M Q, how do we show the isomorphic? Yes, like this one. It's also related to f of M and f of Q. Why? Because f of M is A and f of Q is C. And we really know that there is edge between A and C. A and C. Is there any question about this? Did you understand this one? Yes, no. What I started from M. Briefly saying is this M degree 3 and this guy is degree 3. I went on M to Q, M to N, and M to O. Q, O, N. So M has been connected to Q. Then I chose A to C, E, P in any order. Then I have got this one saying that C to D. Okay. For example, there is C. I can write after here C to D. Or I just wrote N. So I looked at here O, which one? Q. Then I said that, okay, Q, I can make this R and O. From Q to O, from Q to O. Oh my God. From Q, O is already chosen. R. Q, R here. Okay. And from R, so if there is Q, this one R, what is the equivalence of Q is C. I need to look at the C. C, this guy is chosen, this guy is chosen, so I will choose this one D. And with this reasoning, I'm pretty sure that you will be able to solve at least your mid-semester exam question. Not next week, the week after. The week after of next week, in 2 weeks. Beg your pardon. Aloud, please. I have a YouTube video about the mid-semester exam questions. I don't remember them. Now, I will show it. And if it's possible, I will create another YouTube as well. I mean, video. Yeah, it's in my name. You don't have, and also you do not subscribe me, okay? You don't have to. If you like, subscribe, but you don't have to. I mean, it's just for ease, to make the jobs easy. All right, now let's have a look at the Uh, I think until it's 20 minutes. I just want to talk about one last thing. We are unable to finish all the questions. So this one, if you have, what's the meaning of the planar graph is this one. Okay, like the edges are not cutting each other. But here, this one, it's planar. If I K4 is not planar, but if you do like this one, it will be planar. Okay, the edges should not cut each other. The planar graph is the graph such that the edges is not cutting each other. So this is the answer of question 12 by chance. I saw suddenly here, which is matching with my answer. What about this? There is a formula called Euler formula for the graph theory, for the graphs. It's called region, number of the region plus vertices equals to number of edges plus 2. So it's called also face. Instead of the word region, is face is also used. E plus 2. So let's see if this one is working for this one. One region, second, third. Okay. 3. How many vertices do I see here? 1, 2, 3, 4. How many edges do we have here? 4 for the square, 1 for the diagonal, and 1 for the outside curve. So 6. 6 plus 2. So it has to be the same. So this means this was 3 is wrong. In fact, the outside is another region as well. So we have 4 plus 4 equals to 6 plus 2. Okay, so let's do this one now. So K3, question 13. So let's call this one question 12. This is question 11. So the last thing that I'm talking is about the Euler formula. It doesn't mean last question. Question 12, question 13. How many regions do you see here? Any question, any answer? Okay, so there is one region here and one outside. How do you wanna take your, pardon? One inside and one outside. So 2. How many vertices? How many edges? 3 plus 2. So 5 equals 5. So how many here? How many regions do you see here? One here. It's an area trapped, roughly speaking, trapped among the edges. Here as well, 3, and 1 outside. Okay, so it says that question 12, this is the K4, but it's not planar. So the Euler formula is true for planar graph. Okay, so K4 is this one. K4 can be non-isomorphic version of that one. I mean, and this is not it's isomorphic still with the, but this is 3, this is 3, this is 3, this is 3, this is also same as this one. I made a mistake, I said not isomorphic. So this is also K4 because all the edges, possible edges has been drawn for the vertices. Is it planar? Okay. How many regions here do you see here? 1, 2, 3, 4. Okay. Now, what about this one? Now, let's go to the geometry in high school. All right. Look at this one. Okay. So, how many faces do you see in the first picture? This one. So, down, one down. Okay, let's do firstly this one, the smaller one. Let's do this one. 1, 2, the back side and the down. Okay. How many faces do you see for this geometrical object? How many faces do you see for this one? Do you know the meaning of the face? Yeah, for down, here, here, and the one behind that. Yeah. So 4 plus. How many vertices of this geometry has got? 1, 2, 3, 4. This is triangular pyramid. Yeah. Edges 1, 2, 3, 4, 5, 6. 6 plus 2. What's the name of this shape? What's the name of the base one? Oh, no, no, base. The base part with 6-sided. How do you say this one? Do you have this? Huh? Hexagon. Yeah. So there is here hexagon as well. Yeah. In the next to the coffee. So this is called hexagonal pyramid. Yes. So how many faces do you see in the hexagonal pyramid? 7. How many vertices do you see here? 1, 2, 3, 4, 5, 6, 7. How many edges do you see there? 12. Yeah. So 6 on the base and 6 like coming from the point peak. What about this one? Base 1, 1, 2, 1, 2, and 1 down. 5. How many vertices? 5. E plus 2, 8. Yeah. So let now look at here. Do you see this one? How many region here do you see? 1, 2, 3, 4, 5. Okay. It's like geometrical object. It's this one. Uh, Now, uh, edges 1, 2, 3, 4, 5, 6, 7, 8. So 8 here. And vertices 5. So the geometry, you can relate the geometrical objects and graph theory as well. Okay. So the Euler formula is true for graphs. And what's the meaning of tetrahedron? No. Let me see. What about this one? This is called hexagonal pyramid. Sorry, hexagonal bipyramid. So no, it's not bipyramid. It's called hexagonal triple. Okay, I don't know. It's gonna be difficult now. So, but what about this one? You have got bases, like 4 of that. Have got here. But if you get the same thing here, this is called bipyramid. So this guy is bipyramid. So the again, the Euler formula is correct, is true for this one as well, this one as well, for a prism as well. Okay. All right. So let's stop here. This guy. So important topic of today is isomorphic things. So you will get one question about that. And what was it, the previous one? Weighted graph. So you will see. So there are two questions, like few questions about weighted graphs next workshop. Probably I will address you to my videos or I will make new ones. All right, let's stop here. What? Wait a moment.